So let's particularly start with a first-order filter. This is a generic first-order filter. So let's look at its characteristics. There are two things that we normally look at. One is the corner frequency, and in particular, a high-pass filter, we talk about the region where it passes the signals as being the pass band. So the start of the pass band is this corner frequency, omega sub c. And we define it as being equal to 0.707 of the passed band gain. The passed band gain, we call it K sub PB, is a gain at high frequencies. So we'll define it this way. So if I have a generic first-order transfer function that looks like this, my corner frequency is 1 over tau. It is the whatever multiplies by the j omega, and then I invert it. And the passband gain is actually the limit as omega goes to infinity of h of omega. And that's the passband gain. If I look at an inverting high-pass filter, one that gives me isolation, like we talked about in the last lesson, isolation is a good thing. Let's look at the high-pass, the passband gain. Again, I'm going to abuse my notation a bit. If I were to look at the limit as h goes to infinity. In that limit as h goes to infinity, this being h right here, then my 1 becomes negligible, and I've got minus RFC omega over R1C omega. So reducing that down, I get minus RF over R1. And then my corner frequency is, well, I look at whatever constant multiplies by my j omega, and I invert that, 1 over R1C. Now we want to derive this transfer function. Let's go back to thinking about our last lesson. In our last lesson, we looked at a configuration like this, and we said that the transfer function for this is equal to minus ZF over Z1. We derived it in the last lesson. So ZF in this case is RF, and Z1 is equal to the series combination of this, the impedance Z sub C plus R1. And Z sub C is J J 1 over J omega C plus R1. So if I substitute that into this formula, I will be able to derive this transfer function. Let's look at the frequency characteristics of a high-pass filter. So it has this transfer function right here. If I were to look at the magnitude of the transfer function, is right here. Remember that that's the magnitude of the numerator, which is 1, or which is this, over the magnitude of the denominator, which is the real part squared plus imaginary part squared square root. Okay, then I take the angle. Well, I've got a minus 90 because I've got a minus sign and then I've got a j. So the angle of minus j is minus 90. And then this is minus the angle of the denominator. That means in the pass band, we're going to have a gain of this. which is found by taking the limit of this as omega gets very large. Because it's a high pass filter, the pass band is in the high frequency. So as omega gets large, I take the limit and I get minus RF over R1. And then the corner frequency is the frequency at which I get a value that where this imaginary part magnitude is equal to the real part. So that is 1 over R1C. If I were to plot this, this magnitude has to be positive. So this is on a linear scale, so I'm looking at positive values. That's why I have a value of RF over R1 being positive. And plotting the angle, I get this right here. Now, why does this start out at minus 90? Because it starts out at minus 90 there. It ends up at minus 180 because at high frequency, this has a minus value, a minus, and the minus corresponds to minus 180. So that's the angle. And the magnitude, we have the 0.707 value is about right here. So the pass band is considered here, where for the most part we are passing through signals without attenuating them. This is a stop band over here. This is where we are attenuating our signals. The corner frequency, again, is this point right here. That's at the point where we get the 0.707 times this, and the K being the gain of the pass band. So now we want to design a high-pass filter to have a pass band gain of, say, -2, and a corner frequency of 1,000 radians per second. Remember, our transfer function for this filter is minus RFC j omega over R1C j omega plus 1. And my pass band gain is h of omega. When omega goes to infinity, we found that to be equal to minus R sub f over R1. And we want that to equal to -2. Now the other equation we have is our corner frequency, omega c. That's equal to 1 over whatever multiplies this j omega. So that's R1c. And that should be equal to 1,000. Okay. If I've got 3 parameters to choose and only 2 equations. So I can let R1 equal to 1,000 because it's a very common resistor value. So I'll just pick that value. And then I can solve for RF would be equal to 2,000 ohms and C would be equal to 1 microfarad. Now one thing that I want to comment on is if my corner frequency is given in hertz, then I have to make sure that I have this 2 pi factor. Remember that omega is equal to 2 pi f. So omega c is equal to 1 over R1c. So I would have 2 pi f sub c is equal to 1 over R1c. So if my corner frequency is given to hertz. Welcome back to electronics. In this lesson, we will look at times the out, we're given the corner frequency of the pass, and that's 1,000. Pi is equal to 2 pi f. So omega c is equal to 1 over r1c. So I would have 2 pi f sub c is equal to 1 over r1c. So if my corner frequency is given to hertz, I have to convert it to radians per second first before I do this. So in summary, a high-pass filter passes high-frequency components and signals and attenuates or filters out low-frequency components. We looked at one basic design. This is an inverting high-pass filter, and it provides isolation at the input and the output. It has this transfer function right here. And we showed how to do a design. We based the design on 2 factors that are given. If we're given the corner frequency of the passband and passband gain. And then we showed how we were able to pick these parameters. In our next lesson, we will look at more complicated filters, ones where we can build cascaded filters together, put them together and create more interesting filters like passband, or bandpass, and notch filters. Thank you.
Welcome back to Electronics. This is Dr. Robinson. In this lesson, we're going to look at cascaded first-order filters. In your previous lesson, you were introduced to op-amp first-order high-pass filters, and our objectives for this lesson are to introduce cascaded filters and introduce bandpass filter characteristics. Now, before we begin looking at cascaded first-order filters, I want to show you how we can rewrite the transfer functions that you've seen before for the first-order low-pass and the first-order high-pass filters in a different way. I want to write them in terms of Hertz frequency f rather than omega as you've seen them before. Now we know the relationship between omega and frequency is omega is equal to 2 pi f. And from before you have that omega b is equal to 1 over tau is equal to what I'm going to call omega naught, or the minus 3 dB frequency for this filter. And then using this relationship we can write that omega naught is equal to 2 pi f naught. Now I want to make these substitutions into this transfer function to write it in terms of f. So we have h of f is equal to kdc times 1 over j. Now instead of omega I'm going to write 2 pi f, and instead of tau I'm going to write 1 over omega naught, or I can put a 2 pi f naught here plus 1. So we get that h of f is equal to kdc times 1 over jf over f naught plus 1. A completely equivalent way of writing this transfer function for the low-pass filter. Now let's do the same thing for the high-pass filter. We have again that omega is equal to 2 pi f, and from before we have omega c is equal to 1 over tau, and I'm going to call that again omega naught, which is now the minus 3 dB frequency for the high-pass filter. And we have that omega naught would be equal to 2 pi f naught, to put it in terms of f, and from before we have that kpb, the passband gain, is equal to k over tau. Now I'll make the substitutions. We now have h of f is equal to, let me bring the k out front, times j, but I write 2 pi f instead of omega, and here I have j 2 pi f, and we have, just like before, a 2 pi f naught here plus 1. Now I want the quantity sitting out front here to be the passband gain. So I am going to multiply k here by 2 pi f naught, like this. So this would be equal to 2 pi f naught k times j 2 pi f divided by 2 pi f naught divided by j f over f naught plus 1. So I've put a 2 pi f naught out front and a 2 pi f naught here to cancel, and I can identify this 2 pi f naught k as being kpb, or the passband gain, which means that h of f is equal to kpb times j f over f naught divided by j f over f naught plus 1. And you can see in these two transfer functions we have these same denominators, and both transfer functions have been written in terms of f now. Now this is a common way of expressing these transfer functions when analyzing filters, and I'm going to use these expressions for the transfer functions in the remainder of the lesson. lesson. On this slide, I've drawn two circuit topologies that you're familiar with from your previous lessons. This op-amp circuit implements a first-order low-pass filter characteristic, and this op-amp circuit implements a first-order high-pass filter characteristic. If we solve for the ratio of the output voltage to the input voltage for this circuit, we end up with a transfer function of this form. And if we plot the magnitude of this transfer function versus frequency, we end up with a Bode magnitude plot of this shape, a low-pass filter characteristic, where frequencies in this range are passed unattenuated and frequencies in this range are attenuated. Similarly, if we solve for the ratio of output voltage here to input voltage here, we wind up with a high-pass characteristic like this. We plot its magnitude and we get a characteristic of this shape, where higher frequencies are passed unattenuated, but the lower frequencies are attenuated. Let's look at how we can form a more complicated filter by cascading simpler filters. And a cascaded topology means that we apply the output of one filter as the input to the next filter. So in this cascade example, I have cascaded a first-order low-pass filter and a first-order high-pass filter to form the overall cascaded filter. So inside this block could be our op-amp first-order low-pass filter from the previous slide, and this could be our op-amp high-pass filter from the previous slide. Let's label the voltages at various nodes in this block diagram. This would be the output of the first filter. This is the input of the second filter, and this is the overall output of the cascaded filter. Now, by definition, the transfer function of the cascade, H sub C, is equal to V out, the output voltage of the cascade, divided by the input voltage. And we can write that as V out 1 divided by Vn times V out divided by Vn2. Because due to the cascade topology, V out 1 is equal to Vn2. So these two quantities cancel, leaving us with V out over Vn. Now we can identify this term as the transfer function of the low-pass filter, and we can identify this as the transfer function of the high-pass filter. So that overall, the transfer function of the cascade is the product of the low-pass filter transfer function and the high-pass filter transfer function. So in general, the transfer function of any cascaded filter is equal to the product of the transfer functions of the individual filters in the cascade. Let's look at how we can determine the overall Bode magnitude plot for the cascade, knowing the individual Bode magnitude plots of the filters in the cascade. And remember that the output of a filter, V out, is equal to the input to the filter, Vn, times the transfer function of the filter. So the magnitude of the output voltage is equal to the magnitude of the input voltage times the magnitude of the transfer function. So here I have drawn the magnitude of the transfer function for the low-pass filter and the magnitude of the transfer function for the high-pass filter. And let's assume we apply to the input of the cascade a sine wave of frequency 1 Hz and amplitude 1. We can represent that sine wave on this Bode plot as a spike located at frequency 1 Hz and having amplitude 1. We can see that at that frequency, the sine wave is in the pass band of the low-pass filter, so the low-pass filter has no effect. So the output of the low-pass filter is applied to the input of the high-pass filter. This magnitude of 1, frequency of 1 Hz sine wave is applied to the high-pass filter, but it's now in the stop band of the high-pass filter where it's attenuated by a factor of 0.1. So at the output of the high-pass filter, we have a sine wave of amplitude 0.1 and frequency 1. If we apply to the cascade a sine wave of frequency 10 kilohertz, and amplitude 1, we can see that at 10 kilohertz, we are in the stop band of the low-pass filter. The low-pass filter attenuates the signal before it's applied to the high-pass filter by a factor of 0.1. This signal is applied to the high-pass filter where it's multiplied by this gain of 1 and passed to the output. And because of the gain of 1, the high-pass filter has no effect on the input signal. So at the output, we have a sine wave of 0.1. Now, if we apply a sine wave of 70 hertz, this 70 hertz sine wave is in the pass band of the low-pass filter, so it's unaffected. The 70 hertz sine wave is in the pass band of the high-pass filter, so it's unaffected. So the signal passes through the cascade unaffected, up to 1. Now we could do this for